In this module, we will be looking at the propeller system for the ATR. We will start off with an overview. Next, we will look at the propeller control system, including the operation of the auto feather system, overspeed governor, alternate feather system, and the power and condition levers. Finally, we will look at engine starting and the control and indicators of the engine. The propeller is controlled by the Propeller Electronic Control, or PEC. The PEC operates in conjunction with an overspeed governor, an auto feather system, an alternate feather system, a propeller synchrophase system, and the power and condition levers. There is a PEC for each engine. The PEC provides closed-loop control over the pitch change mechanism. In addition to its control function, the PEC manages and isolates any detected system fault. Each PEC consists of two channels. At all times, one channel serves as the master and the other one functions as the backup. The backup channel will automatically take over in the event of a failure of the primary channel. The PEC obtains airspeed and altitude data from the associated EEC. The PEC uses this information along with the current NP value to calculate the correct propeller speed. The Engine Electronic Control Unit, or EEC, provides overspeed protection in the constant speed, flight beta range, and ground beta range by acting on the hydromechanical unit to limit NH. Control is achieved by a stepper motor, which adjusts the fuel flow commanded by the HMU. The PEC controls the propeller pitch angle through the propeller valve module, or PVM. The PVM is mounted on the propeller reduction gearbox. The purpose of the PVM is to meter oil pressure to the pitch change mechanism. The PVM consists of an electro-hydraulic valve that meters oil to the propeller pitch change mechanism and allows normal feathering of the propeller, a protection valve, and a feather solenoid which backs up the electro-hydraulic valve. The PVM manages the basic speed set, beta scheduling, reversing, synchrophasing, and feathering of the propeller. In addition, the PVM provides low pitch protection. The PVM controls propeller blade angle by metering engine oil to one side of the pitch change mechanism in the hub to reduce blade angle, which is opposed by constant oil pressure supplied to the mechanism to increase blade angle. This design allows rapid feathering of the propeller once the unmetered oil supply is dumped. All propeller blade angles are achieved by the controlled metering of oil pressure in the constant speed and beta modes and the dumping of pressure in the feather or propeller overspeed modes. The unmetered oil pressure is always being opposed by the metered oil pressure, which is regulated by a speed sensing governor and then applied to the opposite side of the piston assembly, which controls prop blade angle. Aerodynamic load on the propeller tends to drive the blades to low blade angles. Should the supply of oil pressure to the PVM be lost, a pitch lock feature incorporated into the pitch change mechanism engages to prevent aerodynamic loads from reducing blade angle more than 1 degree and propeller speed increasing more than 2% from the point of oil pressure loss. When the power levers are in the forward thrust range, condition lever input to the propeller valve module sets propeller RPM by adjusting the position of the electro-hydromechanical valve. The set propeller RPM is maintained by the valve metering oil pressure in order to adjust blade angle as required to maintain the set RPM. When the propeller is in the flight governing mode, the propeller blade angle is set by power lever input through the propeller valve module. The propeller valve module also receives mechanical blade angle feedback inputs. As power is reduced in the forward power range sufficient for propeller speed to drop below the PVM setting, the PVM admits full oil pressure to reduce blade angle in an attempt to maintain the set RPM. As the ground beta range is entered, blade angle control transitions to the fuel governing mode. In this mode, the EEC automatically increases fuel flow so as to maintain a minimum propeller speed. This equates to approximately 70.8% NP. In beta range, moving the power lever commands the associated PVM to increase or decrease oil pressure bleed off to move the blades in the required direction. When blade angle has increased or decreased to the new angle set by the power lever, the blade angle feedback acts on the PVM to hold the blades at the new position. Auto feather of a propeller is provided by the Auto Feathering Unit, or AFU. The AFU is a component of the Automatic Takeoff Power Control System. The AFU conditions the torque signal from the engine sensor and drives the needles on the torque indicators located on the flight instruments panel. The AFU also supplies the conditioned torque signal to the Flight Data Acquisition Unit and the multifunction computer. Signal conditioning units supply torque data from a sensor on each engine. The sensor measures torque on the power turbine shaft. The torque measurement system is electronic. The multifunction computer handles the auto feather and uptrim logic. In the event of an engine failure during takeoff, the multifunction computer will command the feathering electric pump to operate and open the feathering solenoid. This delivers the oil pressure required to feather the propeller. In addition, the multifunction computer will also provide an uptrim command to the operating engine's EEC. On the ground, the ATPCS system is armed when the power management selector is in the takeoff position, both power lever angles are above 49 degrees, and both engine torques are above 46%. Since the ATPCS system is armed, the auto feather system will be armed as well. Only the auto feather system is armed if the aircraft is in flight and all the other arming conditions are met. Auto feather is triggered when an armed AFU detects a failure of its associated engine by a decrease of torque below approximately 18%. The triggered AFU immediately signals the multifunction computer, which, in turn, commands a power uptrim signal to the EEC of the opposite engine to initiate power uptrim fuel schedule and illuminate the uptrim green advisory light. The non-affected engine bleed air system is shut down. After a 2.15 second delay, the multifunction computer initiates auto feathering of the low torque engine. This is so reverse thrust can be used on the runway following an engine failure on the takeoff roll. An NP underspeed fuel governing cancel signal to the failed engine's EEC permits propeller operation below the propeller minimum speed without the possibility of propeller engine overtorque. An auxiliary pressure pump is energized and runs for a set time period in order to provide adequate time for propeller feathering before automatically shutting off. Once the auto feather sequence for one of the propellers is initiated, the auto feather system on the remaining engine is disabled, so the ATPCS system cannot auto feather both engines in flight. The auto feather system is disarmed and deactivated by setting the ATPCS push button to off, retarding either power lever below 49 degrees, or by selecting any position other than takeoff on the power management panel. The ATPCS system will also automatically disarm when both engine torques are below 46%. In addition, the auto feather function is also disabled on the operating engine if it has been triggered during an engine failure. Feather mode is initiated either by placing the condition lever in the feather position or by a feather solenoid valve, which is opened normally by the auto feather system. We will now look at the propeller ground range indication and beta backup protection system. Advisory lights are provided on the engine control panel to indicate low propeller blade angle. Marked low pitch, each light is illuminated by a low blade angle switch that is triggered when the actual blade angle is less than the normal flight idle blade angle. These lights will illuminate during ground operations below flight idle. If a low pitch light illuminates while the aircraft is in flight, the CCAS will also be triggered. These indications are the illumination of the engine amber light on the crew alerting panel, the flashing of the master caution light, and a single chime will sound. The propeller valve module uses a solenoid to ensure a low propeller pitch when the associated power lever angle is below flight idle. The components are monitored for each engine by separate sensing circuits. The electronic engine control is monitored for internal faults by fault detection circuits in each EEC. The reduction gearbox oil is monitored for metallic contamination by means of a chip detector. The main oil tank is monitored for metallic contamination by means of a chip detector. Results from the chip detectors are provided only as a maintenance function. There are no cockpit indicators. A pressure detector monitors the differential pressure across the engine oil filter. The purpose of this pressure detector is to detect a restricted or blocked oil filter. The differential pressure across the fuel filter is also monitored by a pressure detector. The purpose of this detector is to detect a restricted or blocked fuel filter. A pressure detector also monitors the differential pressure across the reduction gearbox scavenge filter. The purpose of this detector is to detect a restricted or blocked reduction gearbox scavenge filter. With the exception of the fuel flow indicator, all engine indications are derived from sensors located throughout the engine. The indications are displayed in an analog and digital format. The fuel flow meter derives information from a fuel flow sensor on the engine. This indicator also displays the quantity of fuel used in the digital readout. The NP gauge indicates propeller RPM as sensed by a speed sensor on the reduction gearbox. The values indicated are in percentage of the maximum. Pointer indications are displayed in digital format on an associated display. The range markers on the gauge are marked red, green, and amber. The red radial indicates the maximum RPM. The green arc indicates the normal operating band of 70.8 to 100%. A caution range indicated by an amber arc is to be avoided. This range is from 41.6 to 65%. A test button is used to test the correct operation of the gauge. When pressed, the pointer and indicator will read 115%. A blue dot indicates the 115% position. The NH gauge indicates high-pressure gas generator RPM as a percentage of maximum. This value is sensed by a speed sensor on the accessory gearbox. Pointer indications are displayed in digital format on an associated display. The range markers on the gauge are marked red and green. The red radial on the gauge indicates the maximum normal operation speed of 102.7%. The green arc indicates the normal operating and starting band of 62 to 102.7%. The NH gauge also displays the NL value. NL displays the low-pressure gas generator RPM as a percentage as sensed by a speed sensor in the low-pressure compressor housing. The NL pointer also has colored sectors. The green sector ranges from 62 to 104.2%. The maximum permissible value is indicated by a red radial at 104.2%. A test button is used to test for correct operation of the gauge. When pressed, the NH and NL pointers and indicator will read 115%. The 115% mark is identified by a blue dot. The ITT gauge indicates the ITT temperature sensed by thermocouple sensors between the low-pressure turbine and the power turbine. The ITT reading is also displayed in numerical format on an associated display. An amber light on the gauge illuminates when the maximum operating limit of 800 degrees Celsius is exceeded. This will trigger a CCAS alert, which consists of both master caution lights flashing, the illumination of the engine light on the crew alert panel, and the sounding of a single chime. In the hotel mode, the alert light illuminates when the ITT temperature exceeds 715 degrees Celsius. The range markers on the gauge are marked red and green. The red mark indicates the maximum operating limit of 765 degrees Celsius during normal conditions. The red dot with the H indicates the maximum ITT temperature in the hotel mode. This limit is 715 degrees Celsius. The red dashes indicate the maximum up-trim operating limit of 800 degrees Celsius. The red dot with the S indicates the maximum starting operating limit for a 5-second period. The limit is 950 degrees Celsius. The red point indicates the maximum temperature limit during a 20-second period. This limit is 840 degrees Celsius. The amber sector is the caution range, which ranges from 765 to 800 degrees Celsius. Finally, the green arc indicates the normal operating range of 300 to 765 degrees Celsius. A test button is used to test for correct operation of the gauge. When pressed, the pointer and indicator will read 1150 degrees Celsius. A blue dot indicates the 1150 degrees Celsius position. There are two sensors mounted on the reduction gearbox of each engine. One sensor is used to supply the low torque signal to the auto feathering unit. In turn, the auto feathering unit drives the pointer in the torque indicator. The second torque sensor supplies torque information to the EEC. In turn, the EEC displays the sensed torque value on the digital portion of the torque indicator. If the digital portion of the torque indicator shows a 000, this indicates that the EEC torque sensor has failed. If the digital portion of the torque indicator shows 3 dashes, it indicates that the associated EEC is unable to control the associated handling bleed valve. In this case, the handling bleed valve will be closed. The purpose of the handling bleed valve is to provide good steady-state engine power characteristics as well as an adequate surge margin. If lab is displayed, it indicates that the wrong EEC has been installed. The torque pointer indicates engine torque as sensed by the AFU torque sensor. The range markers on the gauge are marked red, green, and dashed red. The red radial indicates the normal maximum torque of 100%. The green arc indicates the normal operating band of 0 to 100%. A red dashed line indicates the maximum uptrim torque of 106.3%. The maximum torque value is indicated by the red dot at 120%. A test button is used to test for correct operation of the gauge. When pressed, the pointer and indicator will read 115%. A blue dot on the gauge identifies the 115% position. The Flight Data Acquisition Unit calculates a target torque value based on the selection made on the power management panel. This target is indicated by the triangular amber pointer on the outside of the torque gauge. If takeoff is selected, the target indicator will indicate the reserve takeoff torque value. A manual target can also be set by the set knob located on the bottom right-hand side of the torque indicator. This manual target is represented by a white triangular-shaped pointer. The Power Management Panel supplies the Flight Data Acquisition Unit, the Propeller Interface Unit, and the EEC with the desired basic power requirements. This panel is actually made up of two parts. The front part supplies the information to the right engine, and the back part supplies information to the left engine. When making changes on the Power Management Panel, it may take up to 15 seconds for the change to be reflected on the Flight Data Acquisition Unit torque target on the torque indicator. Propeller electronic control unit status is monitored by the 4 lights on the Power Management Panel. The single channel light illuminates in the event one PEC channel fails. In this case, the affected PEC will automatically reconfigure itself to use the operating channel. When each propeller is unfeathered on the ground, the low pitch protection is tested by the associated PEC. During a 2-second period, the backup channel will be used, which will be indicated by the illumination of the single channel light. Provided the system is operating normally, the light will extinguish, indicating that the backup channel is functional. The fault lights illuminate amber, and a CCAS alert is triggered when both channels of a PEC are lost. Releasing the push button out will deactivate the associated PEC, and NP will be blocked at 102% whenever power is sufficient. An engine start panel is located on the overhead panel in the flight compartment. This panel controls the engine ignition system and the engine start system. The start system consists of an engine start switch light marked Start and an engine start select knob. The engine start rotary selector selects the ignition mode and the start sequence. In the off start abort position, the ignition circuit is de-energized and the start circuit is disarmed, or the start sequence is interrupted if the start is in progress. The crank position motors the engine only and ignition is deactivated. This is used in case the engine needs to be cleared of fuel fumes. The 3 start positions enable the start circuitry and select the ignition to use. Click on the start selector to continue. Start A uses exciter A when the aircraft is on the ground. Click on the start selector to continue. Start B uses exciter B when the aircraft is on the ground. Click on the start selector to continue. Start A and B uses both exciters regardless of whether the aircraft is on the ground or in flight. An engine is started by pressing in the desired start push button. The start sequence will start and the starter will engage provided the start selector is in one of the start positions. Starter engagement is verified by the illumination of the associated ON caption in the push button. Pressing the start push button when crank is selected will crank the engine. When the start push button is pressed, the start contactor will close and connect the starter generator to the aircraft main battery through the battery start contactor if the aircraft is on battery power only. If external power is connected, the starter generator will be connected to the external power through the external power contactor and the start contactor. If an engine is already running, the starter generator will be powered by the aircraft main battery and the operating generator, provided the aircraft is on the ground. During the startup, the high-pressure spool is driven by the starter generator to a speed of approximately 20% NH. At 10% NH, fuel is introduced by placing the condition lever out of the fuel shutoff position. At 45% NH, the starter will disengage and ignition is deactivated. In addition, the ON light extinguishes in the start push button. From this point, the engine should now accelerate to a self-sustaining speed. The fault light in the push button will illuminate in the event of a start fault. These faults could be the starter generator remaining engaged after the engine NH speed exceeds 45%, or a failure of the associated GCU during the start. If the fault light for the right engine illuminates, this could also be due to the propeller brake being on while the gust lock is not engaged. The guarded manual ignition push button selects the manual ignition mode. Both igniters will be on continuously when manual ignition has been selected. In this case, the ON caption will illuminate in the push button. This concludes the engine propeller system module.